The next session is on 100% clean energy or 100% clean electricity, the importance of energy sector coupling. And I would like to introduce Dr. Elaine Hart from Sylvan Energy Analytics. Elaine.
Thank you so much, and thanks for coming to this panel. I'm very excited for this session for a few reasons. The first being that I'm leading a task force for ESIG right now on 100% clean energy planning. And one of the questions that has been posed to the task force is, if you focus only on electricity sector analysis, do you get the wrong answer? And so we've got 4 people here who I think who can do our homework for us and tell us if that's the case. In particular, we've got representatives from the United States, from Europe. We're going to be asking them to talk about similarities and differences between the situations in the United States and Europe. We're going to be asking them to speak to how can you hedge against technological uncertainty when almost all of the, if not all of the scenarios that get us to these very ambitious goals involve technologies that are not available at scale today. And we're going to I'm asking them to also speak to, if they're able to, ways of incorporating cross-sectoral interactions from these economy-wide studies in electricity-focused analyses, because I think a lot of the analysis that we do and the analysis that you're hearing about in the other sessions today are primarily, if not completely, focused on the electricity sector, and how can we bring more information into those analyses in a way that sort of is internally consistent and respectful of all the other things going on in the energy economy. So I'm not going to spend more time setting us up. I'd like to just dive right in here. Each presentation is going to be about 20 minutes, and then what I'd love to do is have a wonderful discussion with questions at the very end. So I'm going to hand it over to Chris Clack to get us started.
Thank you. Thank you very much. So I gave a presentation yesterday. I'm Chris Clack. I am the Vice President of Integrated Energy System Planning at Pattern Energy. Some of you may know me from my previous role as the CEO of Vibrant Clean Energy, where we created a model called Wisdom. Everything I talk about here is slightly biased because I'm talking mostly from my experiences with Wisdom. But hopefully there's some themes that will shine through, and I think they're kind of consistent. Disclaimer, I work for Pattern Energy now, so they're a leading renewable energy company. They develop a lot of wind and solar assets across the US. And my role essentially is the same as it was at VCE, but I primarily have one client who I'm answering lots of questions from every timescale, from a few hours out all the way through 2050 at this point. So the first thing I want to just reiterate from yesterday, in case anyone missed it, is that we just released a resource adequacy renewable energy power data set, which is publicly available for everyone. There's a QR code on the screen if you want to go and start diving in. And if anyone wants to follow up, we can send you about, I think, 35 links to different ways to access that data as well. It's an hourly data set, county level. At the moment, it's 2019 through 2023. We're going to do the preceding 5 years in Q1, and then every year we're going to update it with the latest year until the HER stops being produced. And we wanted to try and start filling the gap of open source data sets being available for everyone to get involved with consistent data sets for doing resource adequacy planning and the like as well. And I want to state also that everything that I'm going to show here was using that data set. So trying to be consistent with the results that will come out from this. So Wisdom was originally built as an electricity model. It's weather-informed energy systems, but I always keep thinking the backbone of that is going to be the electricity sector. I don't think that's changed in the 10 years I've been doing this. I think it still will be the backbone. It's how we know how to create clean energy the best. If you look at this diagram, which we did in a paper for Science, the green lines are kind of the traditional transmission lines that you would see. This is kind of a schematic. But all the other lines are connections using different ways of moving energy or products. So hydrogen is blue, liquid fuels is generally purple, and then there's CO2 as well, which can be moved around in what I call shallow cycle. Some of these are a bit far-fetched in terms of how far out you can go, but it does allow us to answer the question what ifs, which is kind of what I feel the point of some of these models is to look at. We don't know until we ask the question. We could just argue it away sometimes, but I think it's better to see whether it's actually going to have any impact. And so we incorporate as much of the rest of the economy as possible. It's a double-edged sword, in my opinion, because the more things that you include, the more assumptions you have to make, and therefore the more mistakes you're going to make. But that's why you have to do scenario hunting and do many, many scenarios. The other thing I do want to push on, because I feel like it is important, and I hopefully will show that the data shows that, is the distribution side. If we are going to do clean economy, we're going to see a lot of loads showing up in the distribution side. And if we're not co-optimizing between these two pieces of the grid, I think we're going to leave a lot of dollar amounts on the table and a lot of opportunity, a lot of inefficiencies built in. And for me, I feel like that's going to be a problem because we don't just have to do this in the US or Europe. We have to do it everywhere in the world for us to be successful. And if we don't do it in a way that uses the least amount of resources, we're going to end up failing. So that's kind of just my personal view. But the real reason in terms of modeling it is I didn't know the answer. And so maybe I was wrong. So I work on the premise of test the hypothesis. If you're wrong, then you can get rid of it. But at least you've tried it and you can keep testing your hypothesis. So just to kind of really explain this sector coupling in the distribution grid. So this is some of the results. So it's mixed up a little bit, but I really want to jump to this piece of how the distribution grid is interacting with the utility scale grid. So the bottom two plots is January and July, and the gray is what's utility filled demand in the distribution grid. So on the bottom, you'll see lots of gray. So most of it's still coming from the utility grid. And there's a bunch of colors on top, and I know it's a bit hard to see, but all that is locally supplied power or storage that's basically reshaping the demand for the utility grid to see. So anything that's colored other than gray in the bottom two is basically local demand, local generation that's supplying the demand. And then on the top two plots, that's the utility scale version of what it's supplying. So the black line you see in both is actually what the interface, as I call it, is being seen. And so in the utility grid, we're still charging and discharging batteries to help with supply and demand. But the model is deciding to reshape the demand that the utilities will see to actually use the distribution grid more efficiently, but also minimize the runaway cost that can happen as you start adding electrified demands. To kind of dig into that a little bit deeper, when we sector couple, we have to start building demands. And this is kind of the double-edged sword I was talking about. As you build up demand, you're making assumptions about how things charge, how people behave. But there are some things that are consistent, and weather is one of the crucial inputs that we keep using, which is why I named the model as such, weather informed. But everything's correlated with the weather, so it's not random. And so here I'm just showing on the left 2020 demand as an 8760, but just kind of doing monthly demand to see how it looks. And then on the right-hand side is just 2050 when we do a clean electric grid. And so you can see demand going up, but there's demand creation and destruction. But in general, you're seeing that the winter is coming up slightly and summer's coming up slightly. So it's getting a bit more weather-driven than it is today, even though it is today. What I'm doing here then is showing the same thing that I showed on the right before on the left, and then on the right I'm showing what the model then decides to do with that demand. So it's reshaping the demand to be more weather driven rather than less weather driven. So hopefully you can see like the sort of hour 0 to 7 in general, which is in Eastern time, is kind of depressed, and then we see a sort of an expanding bubble around when solar peak is happening across the US as well. And so the model itself is dynamic in the way it creates the demands, and it's essentially trying to reshape the demand to supply as well as supply reshaping to demand. And so that's the big thing that the distribution co-optimization does, allows that cost factor to come in about linking across those places. So when you bundle this all together, looking at just electricity, 100% electricity, the left-hand plot here is showing the additional demand that we're seeing from electric storage and distribution co-optimization. So essentially we're adding demand by doing this co-optimization, but it's also shifting it to when there's more supply. And I kind of think of it as a coffin. in the middle of extra demand across the year, which is maybe a bit morbid, but it is what it is. Like you're funneling more demand into the peak hours when there's solar. And this, people can very quickly recognize that this would be risky if there was a big storm that happened or something which would curtail the solar as well, which I'll talk about towards the end. Now, when we add in all the other sectors, and the main sectors I'm talking about is transportation, heating for space and water, agriculture, shipping, aviation. When you add all those in, you get the curve on the left for 2050. So this is a bit far out, but I didn't want to do it too early in the time period because it gets a bit messy. But what you see this big hump now in the early hours compared to the clean electricity version. And on the right, all I did was I just subtracted one from the other, so you could see how much additional demand in megawatts we're adding per month by hour. And so hopefully you can see we're adding a lot more demand in the evening times, and the colors are a bit difficult, but hopefully you'll trust me that the winter ones are the ones that are higher in the evening hours. And we are still adding demand in the middle of the day, but it's much lower than the evenings themselves. And this is before we add any hydrogen into the mix. So this is purely like direct using electrons to supply different parts of the grid. When we then start doing our metrics and calculating things away, what this plot's really trying to show, it's a bit busy, but what I'm trying to show here is this is the change in additional demand when you do co-optimization between clean energy and clean grid. And so what it's really showing is, on average, you're reducing demand when you go to clean economy when it comes outside from the model, because it's able to reshape more of the demand to match more of the weather, because it's much more correlated to the weather. So there are some periods where it's higher, but you're on average reducing demand by about 100 gigawatts, which is a significant proportion of the demand. And you can see on the right-hand plot, which is a colored plot of the changes, there's a lot of negatives, and there's a few regions where it's positive, particularly July and August in the early morning periods just before the sun comes up as well. So the reason I'm showing all this, and I've spent some time on the demands, is like by electrifying and by adding the economy, we're adding structural risk by having more of the economy based on weather. But the point that the model keeps telling us over and over again is that that risk can be mitigated with the fact that it's correlated to the weather, and you can actually use different resources to cover those time periods, and it can actually shift the demand to those time periods more consistently. And then finally, in terms of the demands, we have hydrogen that can come in. In our model, it doesn't ever get picked for electricity production. It's always picked for either producing synthetic fuels, but primarily for making ammonia for food production. It isn't used for an energy carrier in the sense of providing backup generation. It just doesn't ever pencil in the model. And it seems to be heavy-sided towards the early half of the year in our simulations. And I just want to sort of mention this is like a 9-year average. So there is multiple, we're hiding a lot of noise in this. It's all smoothed out. But in general, you see it's producing more when it's sunny and less when it's not sunny. And that's kind of the trend. So I've shown a lot of the demand, but the real thing is what I've tended to concentrate on over the decade is the supply side. So we did a lot of work on getting the demand side of understanding how that relates to weather. And then when we put it through the model, it told us what supply would be needed to meet that. And so on the left, I've got 100% clean electricity, and on the right is 100% clean economy. And I will caveat that 100% here is a hand wavy 100%. It's like 99 point something percent, because otherwise we get ridiculous hockey stick installed capacities, which I'm trying to avoid. So it doesn't look so crazy and so intimidating, even though I feel 3.5 terawatts of generation is somewhat terrifying in 25 years. But on the left is the clean electricity. We see that we have gas going down over time, coal disappearing by 2030. The same thing happens in the clean economy. But what you will notice is that gas stays kind of flat for the decade after 2030. And that's because it's bringing in so much demand that it's actually efficient from a emissions reduction component and cost component to keep those gas plants around and use them rather than retiring them earlier, whereas in the electric grid, it's not the same. And we see a lot of wind and solar in both, but what we see popping out, and both got this option, but we see clean dispatchable generation showing up in the economy-wide solution. And again, I want to caveat that this could be a choice. We dictate how much capacity per year can be installed in the model. So if we allowed it to have hundreds and hundreds of gigawatts of wind and solar being put in, we might not need the clean firm. But again, you might argue that's not a realistic assumption either. And then on top here, we have distributed storage, distributed solar, as well as utility storage, which is the top 800 gigawatts on there. So to make it a bit easier to see what the differences are in the supply stack, I just compared the two. And so I have to remember in my head that we're also supplying a lot more demand here, but we're actually increasing the amount of generation only by net 600 gigawatts. And I say only, it's still a lot, but relative to the 3.6, it's not a huge amount. And we see a lot of switching from solar to wind and distribution solar. And the distribution solar comes in because the electrification is offsetting or deferring some of the need for the distribution asset being built too big. And then we have this clean dispatchable generation. We also notice that the nuclear doesn't go away. The legacy nuclear, it kind of keeps just renewing it. But again, that may be an assumption too far. We do see CCS showing up, and that primarily happens because of the tax incentives that appear that make it lucrative for about 20 years, and then it goes away again. So again, I just think of it as clean dispatchable rather than the exact type. When we then sort of look at the dispatch, I find that doing a full 8760 finds it difficult, but like this is kind of giving a day-by-day snapshot of what the model's trying to do between the different simulations. And hopefully you can see the green, which is wind, and the red, which is solar, are kind of bigger. There's less curtailment in general happening, but we're averaging around 22,000 gigawatt hours per day being supplied to the economy. But we are seeing bigger losses for transmitting the power, and we're also seeing the need for bigger reserves as well. We always make the model look for these periods, which I call the highest stress or the scarcity periods. And ignoring the year on these, because these are 2050, sorry about that, but the left is the clean grid, and this most scarce period is during July, early August, and then on the right, it happens at the end of November, early December time. And you might have to squint, but the yellow bars here is storage dispatching, and you'll see it sort of surrounding a solar on the right-hand plot, and we're seeing 98% of the grid being covered by non-renewable generation. And I want to be clear, in these scenarios, we are allowing a high voltage direct current national system being built. We are allowing co-optimization, we're allowing hydrogen, we're allowing long duration storage, we're allowing not every, but a lot of different technologies to mitigate needing a very small percentage of renewables showing up. But we still get to this period where over these 9 years, we do see a small amount of generation. But the simulation manages to survive it with still 7% of reserves being kept. On the left-hand one, we actually see a week period, one whole week of where the demand is over 80% covered by non-renewable assets as well. And you'll see the peak to trough of the demand is also much higher. But the main reason for showing this is that we go from summer scarcity nationally to a winter scarcity nationally. And we see that they happen primarily when wind dies down on the grid. Another way that I've looked at this and how it looks different is, I call this the storage behavior with system strain. But it's just a way of seeing how the storage is acting as an asset for the whole grid. The system strain, if it's 100%, means that any one unit in any direction, which is bad, will cause a blackout somewhere. And then 0 means there's no chance of that. And it's a confluence of the load factor, the availability of renewables, load forecasts, renewable forecasts, as well as thermal outages. The left-hand side one is the clean grid. And I hope you don't have to squint too hard to see that the clean grid spends much more time above 60% than the clean economy. And in fact, the clean economy only has 3 hours per year on average above the 60%, whereas the clean grid spends nearly 150 hours above that period as well, which equates to about 100 megawatts on the grid needing to go one way or the other for there to be a bit of an issue. And this is a grid that has 2 terawatts to 3 terawatts of generation available to it. So that's a small percentage change. And so I feel like the adding the economy, electrifying more of the economy, adding the weather correlations will actually reduce the risk of these big events happening. And that should be a good thing because the economy is bigger than the electricity grid. So there's more risk to GDP and other pieces too. Other ways that it's different, I've shown this one a little bit before, but it's similar results. It's not quite the same, but it's essentially BAU is kind of what the model thinks is going to happen sort of economically. And then we're forcing it to have a clean grid. That's the green bar. That's the additional amount of megawatt miles that are added. And then the clean economy is adding that blue bar as well. And I just wanted to show, because I don't show this very often, but there's the AC portion, which is the top, and then there's a DC portion as well. And so these two are layered on top of each other to come up with this 350 million megawatt miles additional from 2018. And so we are giving the model the opportunity for all the geographic diversity that the US can get. And then when we sort of do the siting analysis afterwards, this is kind of what it looks like differently by 2050 between the left, which is the clean grid, and the right, which is the clean economy. We see a lot more distributed solar. We see wind showing up more in the Great Plains and less utility solar in the sort of the coastal states. And we see a lot more of this purple, which is the clean firm or the clean dispatchable as well. I know it's a bit hard to see everything, but hopefully you can kind of see the reds and greens is what we're trying to highlight here of where the distribution of those are going. So what does this all mean in terms of like, that's really great. Like maybe it's a bit more reliable. There's a lot of extra work to do all this. What does it mean? So what we wanted to calculate here was what money are we leaving on the table if we don't do it? And so what I tried to calculate here is how much cumulative savings you'd get from doing one scenario versus the other. So we have like traditional modeling, and then we have the coordination with DERs, and so that's kind of about the same cost. And then we have the clean grid with DERs and this co-optimization, and we get about a 500 billion saving by 2050. And then when we electrify the economy, it actually skyrockets to 4.5 trillion by 2050. There's no way we're ever going to capture all those savings or those opportunities, but the fact that there is such a large, or I think it's a large saving, maybe people feel differently, it's worth trying to see how close we could get to that. And the average here is 3.23 cents per kilowatt hour per unit of electricity sold. The biggest saving is in transport, the second biggest is in producing ammonia, and the third saving is in heating. Those big three get us about 80% of the way of the cost savings. And a lot of that savings is due to the co-optimization in the distribution grid as well. So I'll stop there and yeah, move on.
Thanks so much, Chris. Next, we're going to hear from Geoff Blanford from EPRI. One thing I love about this format is that we actually get time to absorb and listen to all of the amazing work that's being done instead of asking people to just whip through it. But it does mean a long session. So after Geoff, we're going to do a brief stretch break before we finish off the second half of this panel.
Great, thanks. Thanks, Elaine. Thanks for the invitation to be here. It's a really fun panel. It's a great conference. My name is Geoff Blanford. I'm with EPRI. I'm in the, it's not me. Here we go. I'm in the Energy Systems and Climate Analysis Group. EPRI is a not-for-profit research company. We work with utilities, other research agencies, government agencies globally to work across technology and analysis issues throughout the energy system. So I want to talk to you about some work we've done answering or looking at, trying to answer similar questions to some of the work Chris has described, and that I think was the motivation for framing this panel around net zero economy-wide pathways. And we've done some analysis where we use an energy system model for the US to look at what it takes to achieve this target by 2050. And I know that the context here is sort of electric sector versus economy-wide. And I want to, I'm gonna pick the right arrow here, here we go. I want to try and frame my remarks in that context. And I think it's a really interesting question. So we're looking at scenarios where the economy-wide net emissions have to get to zero. But what's also happening in on the way is that electric sector emissions are also getting pretty close to zero, maybe not all the way to zero. And so the question is, okay, well, what are the key interactions? What are we learning from this broader perspective of the economy-wide framing that we wouldn't get with an electric sector only framing? And so I think there's three key areas that I want to talk about that come out of our analysis. One is direct electrification. So clearly we know that even without a carbon policy, you could have drivers of increased load from electrification of end use, which is going to have emissions impacts, going to be offsetting direct use of fossil fuels outside the electric sector. You probably have more of that in a net zero scenario. So that's the first pathway. Economy-wide perspective is going to give you more electricity because of more direct electrification. Second one is this idea of indirect electrification. And this is where I think the sector coupling issue comes in. Is electricity a cost-effective pathway to provide non-electric fuels for difficult to electrify end uses or hard to decarbonize sectors? So that one would not be part of the mix if you are only looking at the electric sector, and it could be large. It could also be zero, because there are other ways to get at those hard to electrify end uses. And that brings me to a third point, which is the role of carbon dioxide removal. So CO2 removal is kind of this key, kind of puts the net in the net zero, this key piece of thinking about an economy-wide or cost-effective allocation to achieve a net zero target. If you have these carbon removal options, this really allows you to allocate some positive emissions while offsetting them with negative emissions. And I'm talking about not just direct air capture, but also bioenergy with CCS. So if you're using a biofuel, capturing CCS, or if you're producing electricity or hydrogen from bioenergy, capturing that carbon that was atmosphere neutral, you're storing it underground, creates a negative flow. So that creates synergies in terms of carbon management that allows, I think, a more flexible allocation of effort. So that's kind of a key theme throughout all this analysis, is the role of those CDR technologies. And if you're looking at electric sector only, you might not see that whole suite of CDR options, and you might not think about the trade-offs between, say, 100% and net zero differently. Okay, so this is my version of the chart that Chris showed. So I guess it's a plan view. Don't have the third dimension, but a lot of similar pathways and icons. So this is a description of all of the pathways and sort of sector interactions that we're considering in our model. There's actually a lot of detail, technology and sectoral detail beneath this figure, but at a high level, these are the kind of pathways. And electric sector, one of the things that visually jumps out of this is, okay, we all think about the electric sector a lot, but it's just that one icon up there in the left-hand corner. It's got a lot of arrows connected to it. It's really important. I agree with Chris in terms of characterizing it as a backbone of a lot of these scenarios of the energy system transition. But it is, just part of it. And of course, it's a minority of CO2 emissions and total energy when you think about the total system. So the kind of key question here is, well, how can I use that sort of lightning bolt to kind of decarbonize all of these flows throughout the economy? So the model's looking across all of these pathways. It doesn't use all these arrows necessarily, but each of them is sort of costed out and characterized with future technology assumptions. As Chris mentioned, a lot of assumptions means a lot of places to be wrong. But you want to do the best you can, do sensitivities, and then put this in a framework where you can sort of really think through what the economic trade-offs are across these different pathways. The modeling framework that we use to do that is called the US Regen model. I'm not going to talk a lot about it, but it is a detailed energy system model. It started out as electric sector, and then we added through research over the last few years, this, first of all, the end use model that's characterizing technologies at the end use side. So you're integrating those decisions with decisions on the supply side. And then this set of non-electric fuel pathways and decarbonization options like hydrogen, synthetic fuels, and biofuels and the related carbon management. Okay, so those are the options in the model. Please go to our documentation link if you want to know more. This is the study that we did a couple years ago, and we're about to release an update of it. I'll give you a preview of that. And I just want to, first of all, it is publicly available if you want to follow that code, which is not very visible, but that link is active. You can read the whole thing in painful detail on the web. This slide kind of highlights the scenarios that we're looking at here. And I want to highlight this key difference between what we've called the all option scenario and the limited option scenario. This is a small number of scenarios, but it makes a key point, this distinction, which is If you don't have CCS available, and that's the key thing about limited options, also it's more restricted in the bioenergy supply. This really limits your ability, or completely limits your ability to do certain CDR technology. So if you're not storing carbon underground, can't do CCS anywhere, what this does is creates much more incentive or requirement to do direct CO2 reductions or direct fossil fuel replacement. So it puts more pressure on direct electrification, and it creates more need or more demand for indirect electrification. It also limits your options in the electric sector for what that sort of firm capacity can be if you're limited in terms of CDR supply. So these two scenarios are kind of like a difference between a net zero and 100% clean energy, because in the limited options, you really have to get almost all the way there. We don't have non-fossil technologies for everything, so you can't get all the way there. So we have a little bit of CDR from natural climate solutions like afforestation, but we only allow a small amount of that. So it's sort of a clean economy-wide energy, and the limited options is where you're forced to get. So that draws a lot of contrast and creates a lot of creates two very different pathways to net zero. And so that's where I want to sort of talk about these key themes for how the electric sector perspective is different when you have this economy-wide frame. Okay, so I want, as I mentioned, there's a lot of detail here, but I want to talk sort of at the high level. So most of these slides and results I want to share are kind of the aggregate, what's happening at the aggregate level US-wide. So I'm going to start with emissions. So current emissions, about 5 billion tons. In a reference case, which is no new carbon policies, so it does have state policies, or existing policies, but we see a lot of electrification, so you are reducing emissions. But electric sector, even though it's serving a lot more load through particular transport electrification, still a lot of fossil, still a lot of gas in a reference case. So you're only getting maybe sort of halfway there. Still, it's a lot of progress. But if you think about what would need to happen from there to net zero, there's sort of two things happening. One is the electric sector is getting decarbonized. And the second is you've got that section of non-electric emissions that needs to either be reduced or offset. And so what you see, if we go to the net zero cases in that all option scenario, we get to about 1 billion tons of positive emissions remaining. So that, say, roughly 2 billion tons of non-electric sector emissions gets down to about 1 billion. So we cut about half of them through fuel switching, efficiency, electrification. But the other half, it's more cost effective to offset with negative emissions from CDR. In particular, this biofuels CCS pathway. Right? Biofuels are sort of doing double duty. They're offsetting petroleum as well as providing a carbon offset. Electric sector emissions, meanwhile, are going almost all the way to zero, but not quite to zero. It's about a 97% reduction. So because you have this CDR option, there's this sort of assumption that you're able to balance emissions anywhere in the economy with negative emissions elsewhere. It means you can have a little bit of gas left in the electric sector, and you're still achieving economy-wide net zero. And that's like very different than 100% clean energy within the electric sector. It avoids a lot of costs, right? You see the carbon price here is $165 a ton. That's a model outcome for this scenario. That's pretty low, I think, for a economy-wide net zero. It's pretty high relative to any market we see today. But as far as the marginal cost of achieving such a deep target, that's pretty good. Of course, conditional on all our assumptions, which are probably wrong. But the idea is that with this CDR flexibility, you avoid going up the cost asymptote. That can happen when you're really trying to get the last sort of ton out. And you avoid that asymptote in both the electric sector and the economy-wide or the non-electric sectors. Okay, so contrast that with the limited options case where you don't have CCR, you only have a little bit of CDR, which we sort of keep in for feasibility because of these sectors that don't have mitigation options. So your industry and your fuel sectors like chemicals and cement, a couple of things that would have some residual fossil emissions. Everything else pretty much goes away, including in the electric sector. And the way this happens is through much more electrification, direct electrification, but also through hydrogen-derived fuels that are produced through electricity. So this is a pathway using indirect electrification as well as direct that can get to nearly 100% clean electricity or clean energy economy-wide, but it's very expensive at the margin because you're really pushing down these pathways, which are capital intensive, they're pretty inefficient, and we're going to talk a little bit more about what these synthetic pathways look like in terms of energy use. But really, you're pushing very far up this cost asymptote to get those last tons out. And what happens in the electric sector, because you're relying on this indirect electrification pathway, is much, much more electricity demand. So that's what I want to talk about next. So this is what's happening on the emission side, and that's kind of the key difference in these strategies. So this is final energy. So this is the delivered energy total across the economy. So it's not including the energy that was used to produce the fuels, just the delivered BTUs. So electricity increases from today by a lot in all scenarios. In the net zero case, you get to a little over 40% direct of final energy is electricity. When we go into the limited options and this higher fuel cost, something in the middle, you're getting up to almost 60% direct electrification. So this is a lot more, particularly of buildings and industry, which maybe weren't as cost effective in the all options case, but then become more cost effective when you're putting a higher premium on carbon. Still not 100% electrification. There's still some molecules being delivered. So that's gas and liquid fuels and some hydrogen delivered directly. But if you see the pie charts at the top, these are showing what's happening to the fuel mix in those delivered gas and liquid fuel networks. So these are drop-in equivalent sort of mixes that include biofuels. That's the RNG or the biofuels and the liquids, and then also synthetic fuel. So this is a electrolytic hydrogen combined with a biogenic carbon to form a hydrocarbon that is essentially carbon neutral, allows you to meet these non-electric demands in a zero carbon way without relying on CCS. So this is sort of the e-fuel pathway. And this, again, relies heavily on the electric sector. So here we're getting, if you count the direct hydrogen and the synthetic fuel that are hydrogen derived, about 20% of final energy is coming from this pathway, and about 60% direct. So 80% of final energy is now coming from the electric sector, as opposed to about 40% in the all options case. So that's, again, that distinction between net zero and sort of 100% is a big one in terms of electricity demand. So this is what we're looking at in terms of total electricity. Focusing on the all options case, there's an increase to about a little under, or maybe 5,500 terawatt hours, modest increase from today, some efficiency offsetting efficiency or electrification growth from transportation. But then in the limited options case, much higher demand across all the end use sectors, and then this huge demand from electrolysis. And it's important to mention this electrolysis pathway is really inefficient, right? So you're offsetting much more non-electric demand with that sort of green going into electric transportation directly than you are with the pink, which is going into hydrogen, and then again into synthetic fuels, more conversion losses. So that pink is supplying sort of 20% of final energy, whereas the rest of it is supplying 60% of final energy. So this pathway of indirect electrification is costly, it's inefficient, but it's your only option in this case. So this is kind of where we find ourselves when you think about different pathways. It's like, okay, this technology is possible. It could be a big role for the electric sector, but do we necessarily want it to be when there's these options for carbon management at lower costs? Another thing to note, and Chris mentioned this too, almost none of the hydrogen is going back into the electric sector, right? It's almost all going to non-electric. So there's a little bit of generation from hydrogen is used for firming capacity, but almost all of it is to decarbonize non-electric sectors. Okay, so the other side of that generation coin, I didn't talk about the generation mix, but maybe I'll just go back. The generation mix is obviously much larger, and it's much more renewable heavy when we're trying to do a lot more electrolysis. In the all options case, we have a sort of more balanced mix of nuclear, CCS, and renewables. Renewables about 50%, whereas in the limited options case, it's much larger and it's much more renewables heavy. There's also more nuclear because CCS is not available. The big increase in renewables is because you're trying to supply this electrolytic hydrogen, right? This is not being supplied by curtailed energy, right? It's being supplied by dedicated new wind and solar resources. And I'll show a picture of what that looks like from a dispatch. Okay, and this is what's happening on the capacity side. Just a key point to make here, all of this renewable capacity is basically supplying energy, but not firm. So this capacity at the bottom is really what's supplying, is there to meet peak loads and the sort of moments when we know renewables will not be there, or when net load will be close to peak load. So that includes storage, but also gas. So there's new gas in all of these scenarios. Used infrequently. In the all options case, you can use it with fossil gas. In the limited options case, it's being used with RNG or synthetic natural gas. But this gas capacity plays a key role. Okay, just a few more pictures that I think maybe give you that full perspective. So this is a Sankey diagram starting with today. This kind of will echo some of the things I just showed, but kind of put it all in one chart. So this is what happens in the all options case. Big increase in electricity going to transport, big increase in biofuels. That capture from the biofuels is what's fueling the CDR offset. And then gas still has this big role, right? So the gas size of the gas demand overall is pretty similar to the reference case. Liquid fuels, petroleum is a different story. Now, everything changes when this limited options case. So the kind of everything gets rescaled. Now we're doing bigger blue areas into all the end use sectors. And now we're this hydrogen or this big blue arrow coming back into hydrogen, now going into some direct use in industry, but also into the synthetic fuels. And you can see how the arrows keep getting thinner as you work down, right, from the from the renewables into electricity into hydrogen to synthetic fuels. That's all the losses that are involved in this pathway, which is one of the reasons that you're trying to do just a little bit of final energy ends up being a lot of electricity through this pathway. Okay, so last thing to mention is sort of what's happening on a dispatch basis. So this is showing a sample week in the limited options case when electrolytic production is trying to align itself with the renewables. This is sort of the lowest cost. This is an SPP, wind heavy region or high quality wind region. So you've added a ton of wind and then aligned the electrolytic hydrogen production with the wind. That black line is sort of all the other loads, and then the pink is the absorption into electrolysis. So this is kind of by far the biggest load on the system. Again, a lot of the synthetic fuel production is actually located in these regions. So this region has become a big exporter of power and of e-fuels. But this is, operationally, this is, other people at EPRI look at this and say, well, you're going to be kidding me. Like, this is not possible, right? How does a system like this operate? And I don't know whether that is even feasible, but this is what the model does with it. Balancing is coming from the flexible operation of electrolysis and also from battery storage. There are other weeks when you do use a little bit of gas and hydrogen to firm some deep holes. That's actually a pretty good renewable week, although it gets a little bit dicey there at the end. We've also done some analysis of 45V, but I'll skip that if somebody wants to ask a question. Hydrogen storage is completely different with a 45V incentive, which was not part of the net zero scenario. Okay, the final point, I will just preview our new net zero update called Net Zero 2.0 scenarios, where we looked at a bunch of different cases. This is just kind of showing this point about electricity demand increasing in all scenarios. We did add sort of data center scenarios in this one. And you see this, the high end of that range is really driven by the potential for big demands from electrolysis in case of a sort of limited option scenario where you're really forced into these e-fuel pathways to decarbonize those sectors that they really don't have any other options. So in a lot of scenarios, you may not be doing any e-fuels, but when you are doing it, it can be a very large load. But direct electrification of EVs and data centers are going to be big drivers, I think, in all of these scenarios going forward, certainly compared to the recent history. Okay, just want to recap these points and then I'll stop. I think we're at 20 minutes, so if you're eager for your stretch break, I'm almost done. These are the things that I think are really important that you learn from an economy-wide net zero analysis about the role of the electric sector that you might not have learned if you're only focused on kind of what's happening to decarbonizing the generation mix. So first of all, increased electricity demand is a key theme. Direct electrification, you're probably going to be doing more of it if you're trying to decarbonize the end use sectors, so you might be doing a lot of it anyway. And then the second is this indirect electrification story, which I've mentioned could be a major driver, but really is only if you're in a limited CDR world, which could very well be, because I don't know how people feel about CDR in general and this kind of flexibility to offset emissions. I think opportunities for CDR are really, really important for how the electric sector decarbonizes this availability of low carbon fuels, right? You need this firm capacity that runs infrequently. That's kind of a key piece of all of these systems. Even if you're doing a lot of low carbon baseload and renewables, there's still going to be, and storage, there's still going to be deep holes that are going to be met with something, dispatchable that doesn't run very often. And so having this range of low carbon fuel options like hydrogen or RNG or synthetic fuels, or even conventional fuels with CDR offsets is, I think, going to be key. So some combination of those options is going to be needed. And supply of those is really a key interaction with the non-electric sectors in that economy-wide perspective. I'll stop there. Thank you very much for letting me go over a little bit and look forward to your questions. Okay, thanks.
Thanks so much, Geoff. Okay, for our stretch break, I'd like you to channel your favorite figure you've seen. You can be a Sankey diagram. You can be the hockey stick on the way to 100% clean electricity. Just move a little bit. I see we're nearing the end of the day here. Want to make sure we've got enough blood going to our brains. Okay. All right, next up, we've got Peter Markussen from Energinet in Denmark. Really excited to hear the European perspective on these topics.
Yeah, thank you very much for that, Elaine. And yeah, I'm so lucky that I can keep standing up and stretch. So yeah, my name is Peter Markussen, and I'm from the Danish transmission system operator. And but what I will present here is a short introduction to Energinet, where we have the responsibility for both electricity, gas, and also to look at hydrogen. So we are trying to do this sector coupling to live the pathway. And I will try to show how do we do that actually already now. And I know some presentations on where is it we're supposed to be in 2050. And I think one of my key points is that if you want to be there in 2050, you have to start now. You cannot wait to 2030 or 40 to do something. You actually have to look at this sector coupling right now. And I will give some examples on how we now try to work with this. I'm not sure we have the right solution yet, but just shows that to show what we are trying to do. So this is Denmark. We have Norway, Sweden, Germany, Holland, and also UK are we now connected to with a 756 kilometer long HVDC offshore cable. It's the world's longest, was commissioned here in 2023. So I think some years ago, not many people thought it would make sense to make such a long HVDC cable, but it does. And now there is actually projects that are even longer being planned. Just to say that already now we are stretching technology and find out that we can already do more with what we already have. As mentioned, we have the responsibility for gas and electricity, and the green is the electricity and the yellow one is the gas. And we have a pipeline to Poland. It was also commissioned here in 2022. Actually, it was around the same time as Russia invaded the Ukraine. So now we are supplying around 25% of all natural gas to Poland and to make them independent of the gas from Russia. So that was a good decision, especially made by our Polish partners back in 2014. But again, to say that you need to be maybe 10 years ahead with your decision to have them when you actually need them. So we are also looking at offshore wind. We have a number of offshore wind parks in Denmark, and we are planning new one. That's the yellow one, where we're also looking at energy hubs out in the North Sea with 10-20 gigawatt of offshore wind. And I would say that's the resource we have in Denmark. So yes, currently we have oil and gas also in the North Sea, and we use that and export it. But in the future, our resource will also come from the North Sea, but it will be offshore wind. But maybe in other states where you're from, here in the US, it might be solar or You might have other resources. I even heard that there might be natural hydrogen that you can actually use in the same way as you have fracking of gas. I don't know much of that, but maybe that's a new possibility as well. So we have the responsibility for the day-to-day balancing, and we are owned by the Danish Ministry of Climate and Utilities. We are non-profit, and we are now approximately 2,500 employees. Just 3-4 years ago, we were only half of that, but due to all the projects we have with the green transition, and now I say green, not clean, because it is green, what we try to do in Denmark. There are many projects, but also our whole IT system, the whole complexity in our system. We need a lot of new IT systems, and we are trying to develop that as well. And there is also a cybersecurity issue, so therefore we need more hands. So today we have a consumption around 33 terawatt hours. Around 65% of that is from wind and solar. Wind is around 50%, and then some solar. We have thermal power plants. Most of them is biomass, wood chips, wood pellets, and they are also delivering district heating. And then we are also some imports. It doesn't mean that we don't have capacity enough to cover our own consumption. It just means that it was cheaper for us to actually import from neighboring countries than to produce it ourselves. And then Denmark is split in two. We are part of both the Nordic synchronous area and a European synchronous area. The stipulated line, you can see where we have the split. So in Western Denmark, we actually have then up to 77% of solar and wind in the system. Quite a large share, but then also quite dependent then on our neighboring countries for flexibility and balancing. So when we then look at the development in Denmark, we have decreased the emission of CO2 quite a lot in the last years, but now it starts to get more difficult. We are reaching the hard to reduce solutions, and that then include, for example, hydrogen and also more sector coupling. So, and if we look at then the whole energy system, as you can see in the figure to the right, then we have 50% green energy today. You saw it was 65 in our electricity system, but it's a very high share of green energy in our district heating. More than 60% of all households in Denmark, they have district heating, and it's from biomass boilers, also biomass-fired combined heat and power plants that is delivering that, but now also to a larger share electric boilers and large-scale heat pumps that is delivering it. And we still use a lot of oil. That's mainly for transport, also industry, and still some gas also for household heating, for electricity, and also for industry. So we are now at 50% in total, but we now need to look at the hard to abate sectors. And I have listed the many things we have done to reach where we are today, but in the future, the sector coupling will be the most important solution to look at and to get the flexibility into the system and reduce the use of fossil fuels in the hard to abate sectors. So, and so this is the energy sector. Just a short word on other things we do for CO2 reductions, because we have actually just introduced a CO2 tax on agriculture to reduce the emissions from agriculture, from pigs and cows. So it is possible to do something. Then we also looked at direct air capture, but actually that has been reduced a bit in the last political planning for the future. And instead there is a more focus on the carbon capture from large point sources as cement production and also still some power plants. And then it will be stored in old oil fields in the North Sea. That's the current plan. So the flexibility, and this is from a week here in 2024 in April. And if you look at the dark line, the top dark line. Then you have the total consumption. Then the red part, that's then the flexibility from the power to heat. Then the stipulated line is the power price, the day ahead price. We have a European power market with a Danish price of that. The green one is in the wind, and the yellow one is the PV production. And as you can see, there are times where we then actually, or hours where we import, hours where we export, and depending also on the price, you see the increase in the demand, and especially now in the district heating, where we have the possibility to actually increase a lot. We have up more than 1 gigawatt of these electric boilers, and also with the large heat pump, we have now around 0.5 gigawatt. So they can actually be quite flexible. And this is really helping our system. And we are also in dialogue with investors in electrolyzers and also manufacturers of electrolyzers. We have done some testing, and our assumption is that electrolyzers can go down to around 10% of capacity. They cannot shut down totally, but 10% of capacity. And then they can quite fast also ramp up to 100, but even 110%, they actually have some overload potential as well. So they can give the flexibility. The constraints might then be in their storage of the hydrogen, or if they are converting it to green ammonia or to other kinds of fuels. That might be a larger constraint in the flexibility, but the electrolyzer itself is actually quite flexible. What we also see is that we can have quite low electricity prices. As you can see on this Sunday, we almost had prices around zero, where now a lot of solar, especially solar, is built on market basis. So they don't get any support. They actually shut down production, so they have a voluntary curtailment. And we expect that to increase, and it's not necessarily bad to have this voluntary curtailment. I also saw in your analysis, you expected to have curtailment. And actually, when we do our analysis to the future, we might accept up to 15% of curtailment, or we'll actually say that is economically a good idea to do the curtailment. Then actually to build more solar, so you can deliver more solar when the sun is getting up and sun is getting down, and then shut down during the day where there might not be that large a need of it. So that's also something we try to include in the modeling and say, what's the optimal level of, you can say, commercial curtailment. So yeah, so flexibility, that's very important. And you can say sector coupling. Here we already have the example with district heating, but we also expect to see that with power to X, or with electrolyzers. So what does our future look like in Denmark? This is the consumption, and as you can see, a very large increase, especially in electricity for producing hydrogen. The reason for this is that we have this quite good resource of offshore wind. It's shallow water, it's relatively close to shore. And then the plan is to convert that into hydrogen and export to Germany. We are very close to Germany. We have existing gas pipelines that we might be able to use. So that is the plan. So, but there will also be electrification for our district heating, for transport. We also see data centers. It was quite interesting to hear about data centers earlier today, and also the potential flexibility in data centers. And then the generation, there will be a lot of offshore wind, but we also expect a lot of solar. And I think it was quite interesting to see how much wind versus solar will you see in the future. And so currently there is a lot of focus on solar in Denmark or in Europe in general, because it is very cheap. But you can say the value of wind electricity might be higher because you have a better profile. They produce more during the year, and also when the sun is not shining. So this might change, but currently based on the prices for solar and the prices for land, and actually also the NIMBY effect of wind, that it is less for solar. So we expect to see much more solar. But then we also have our gas system, and a bit unusual in Europe is that we actually expect to have 100% biomethane in our consumption already from around 2030. That's biomethane from the agricultural sector, from the forest industry, households, so in that sense, we will still have use gas. We can use that gas then for industry, probably not for heating, but can also be used for producing electricity, backup or reserves. But as you can also see, we expect a quite fast reduction in the use of gas, and that's especially for heating in households that are now being converted to district heating. So this is our future. So how to move on? What's then the prerequisites that we see and we focus on? And here there is a quite simple picture of the very detailed pictures we saw for the US in the same way, and where we then see 4 issues that we focus on. And one is power grid must be expanded, but also it must be utilized in the best possible way. And you say you can connect a solar farm and it produces maybe 1,500 hours per year. And then the rest of the time, couldn't you then use the grid for something else, or you use it better? So that's one question. Then also there is the ancillary services, the whole balancing. We need to focus on that. And then finally, also the gas grid needs still to be competitive. We must make sure that we use the gas resources we have. And here it is the biomethane, but also the hydrogen. Make sure that hydrogen is competitive so that we only use it where it creates the most value. And here we don't expect to use hydrogen to produce electricity, because that's a way too expensive fuel to use for that. We should use hydrogen for the industry, fuel for sea transport, for air transport. So that's what we try to focus on. And we then do our long-term development plan and say, okay, how do we coordinate this? And to the left is then development of our electricity grids. We already have a number of connections to neighboring countries, but we need a lot of grid, especially in the western part of Denmark. And there we then try to use both the existing corridors and increase them, not to influence too many of the landowners in the area. But then the hydrogen transmission, and here I think it's important to notice that it's actually in the same place where we're also increasing the electricity grid, because it is there where we expect to connect a lot of the offshore wind and also a lot of the solar. So then you have the possibility both to send something as electricity, but also part of it as hydrogen. And also we hope that the investors and the electrolyzers, they will then locate close to the west coast. I'm not sure if I can. Yeah, I can show it with the arrow here. So there's up here and there is down here. And where we will start is this, what we call the lower T, where we will have a lot of offshore wind coming in here and potential electrolyzer projects. And also we see a large project here. And here you also have big harbors in both ends, and then to export to Germany. And we already have 2 gas pipes from here down to Germany, and one of them might be able to be used for hydrogen. And actually, we have cut out a part of it and sent here to the US to make investigations if it can be used for hydrogen. There's a political decision for doing this, and also there is a support for those that are going to invest in the electrolyzers to use a minimum part of this capacity. So we expect that in 2032, it's now 4 years later than we expected a year ago, but still in 2032, we expect then to have this lower T transmission hydrogen pipeline to Germany. And then gas transmission, not many changes there, but our challenge there is then to upgrade the biogas to biomethane and pressurize it to the transmission grid. So that is our long-term planning here. And then just for one example then on how to try to do this in practice, because we have all the offshore wind tenders. It's a bit different than in the US, where you have lease areas. In Denmark, we have tenders where you then give a bid on what you would like to pay to actually then build the transmission, and then you are also promised that you have a grid connection. So there is 6 times 1 gigawatt of projects. We as a transmission operator, we promise to make 1 gigawatt available, but you have this potential for overplanting. So if you want to build 1.4 gigawatt or 1.5 gigawatt, you can do that, but your grid connection is only 1 gigawatt. But then, you say before the connection, you can then connect with electrolyzers, or you can also put in storage, or you can put in maybe also a solar farm if you want to do that with a different profile, so that you can utilize this grid connection better. So that's part of the tender that is ongoing right now. The tender has a deadline here at the end of the year, and we are quite excited to see if someone wants to utilize this overplanting possibility to produce the hydrogen or to introduce storage or whatever they want to do. But it is a good possibility to produce the green electricity that then should be used for the hydrogen. Our focus is on then establishing this hydrogen backbone, and also then on the longer term, look at hydrogen storage to make sure that we have the flexibility in the system, because this hydrogen storage, that's enormous amounts of energy you can store there compared to a battery or other kinds of storage. And also it can be used as a seasonal storage. So that will be quite important in our future planning. So this was some examples on what is it that we're trying to do already right now to make sure that we can have the sector coupling, and also make sure we move towards the long-term pathway, not just in Denmark, but actually in Europe. So I think this was the last one. So thank you.
All right, thanks so much. Next up, our final presenter here is Ryan Jones from Evolved Energy Research.
Thanks, Elaine, and thank you to ESIG for the invitation to be here and organizing this panel. I'm really glad that we have somebody from Europe on the panel here, because they're so far ahead of us in the US on this question of sectoral coupling. So I'm impressed with the x-axis and all the charts that, we're going to do this in 2031, 2032. It's, frankly inspiring. So my name is Ryan Jones. I'm the co-founder of Evolved Energy Research, and we investigate questions that arise from basically an energy system transition, and that either is because of new technology, or a lot of our work focuses on kind of ambitious carbon targets here in the US and also in Europe. I'm going to try to convince everybody in the room today that they should be doing all of their electricity sector planning from an economy-wide perspective, right? So my goal is just to show how important it is here to take the sectoral coupling piece into account when we do, when we run capacity expansion models from a utilities perspective. We also do a little bit of work both in the US and in Europe, and I'm going to try to kind of show some contrasting results between the two of them. And then there's also this, another question that's come up in some of the ESIG discussions recently are around these emissions target setting for the electricity system. So I want to kind of tease this piece apart too, which is, what does it look like to have 100% clean target in electricity? And then what if you had, an efficient carbon market and broaden that target to be a bit wider? The comments that I'm going to speak to today really draw from our annual decarbonization perspective. And we've got a forthcoming 2024 report. Our US work is funded by Breakthrough Energy, and we have a European report funded by Third Way. And I'll just highlight here, in the spirit of kind of Chris sharing some of the weather data that his team is producing. I want to highlight this data set that we put out with the annual decarbonization perspective every year that has at a state level many different outputs that could be of interest to the ESIG audience for folks in the room. And some of this data has been, I think, successfully incorporated into some of the latest studies coming out of NREL and others. So kind of the obligatory caveat here, which is, we're looking out to 2050. It's the Eisenhower quote. It's always what this reminds me of, which is plans are useless, but planning is indispensable. And so with that caveat, really what I'm going to try to do is take our model and do some what if analyses, and I want to show you the results of those today. I won't belabor this, but the important part to mention here is, like some of my fellow panelists, the model we're using on the supply side is a kind of economy-wide linear program. It does an optimization. It's got perfect foresight out to 2050, and can help tease apart some of these scenario input assumptions. So I've got 3 scenarios here that we ran, and these are I think similar in some ways to what some of the other models you just heard about are doing. On the left, I've got a clean electricity scenario. On the right, I've got a clean economy scenario. And in the middle, I've got a scenario that kind of combines the two of them together. So for the two on the left, we have a policy scenario that we put in the model, say you have to have 100% clean generation by 2040. And the two on the right, we also impose an additional constraint that says you got to be net zero CO2e, so it has kind of non-CO2 emissions as well, and land sink. So this is kind of an atmospheric stabilization scenario there on the right. So everything else in the capacity expansion model is exactly the same, but at the bottom, I'm showing the final energy demand that Geoff kind of explained. For each of these are high electrification scenarios. So we are in just direct electricity consumption, we are doubling electricity by 2050. This is a little bit higher than a lot of our work in the past, because this includes some data center projections, right, that have kind of moved up a lot of this load growth. Like Geoff's, we get to about 50% consumption on a final energy basis coming from electricity. Okay, so now we run those 3 scenarios through the capacity expansion model, and I want to kind of tease apart some of the key differences here. So the big thing that you see right away is that the difference in generation between clean electricity and the net zero economy scenario, I think all of the panelists we've had very consistent messages on that. The 2,000 terawatt hours may not sound like a lot. I learned this morning that's equivalent to 80 Googles worth of electricity consumption, right? So this is, not that anybody in the room needs to be told that we need to build more wind and solar, right? But this economy-wide perspective, I think, really puts into stark relief the challenge that we have in front of us on the generation planning side. And then there's an orange wedge here that are industrial boilers or basically use of electricity for steam production. If you look at final energy from industry, the biggest heat demand in industry is steam. It's low temperature, it's easy to store, and there's a lot of different interesting technologies that can operate flexibly within that space. And then the hydrogen electrolysis there on the top. On the clean electricity case on the left, we've got a little bit of hydrogen used in gas power plants, but on the right, the vast majority of this hydrogen is used for other places to decarbonize other sectors, right? So we've got e-fuels, we have ammonia production. And the thing to stress here is that it's not enough in the capacity expansion models to just put electrolysis and the electrolyzer back to a gas power plant pathway within that modeling, right? It's the fact that we have these additional loads for hydrogen that I think really makes all the difference here on the planning side. On the generation side, and this is one place where Chris and I's model might be disagreeing at the moment, which is in clean electricity only, that's where we are seeing the most clean firm capacity, right? So the gas with carbon capture is down there in the kind of light gray at the bottom. Overall, that system delivers 74% of the energy as kind of variable generation, wind and solar. If you go to the clean economy there in the middle, we go all the way up to 82% wind and solar. And if you look at that kind of share of gas with carbon capture, that goes down, right? Part of what the electrolysis does for you is it gives you a resource that can operate very flexibly, right? As Peter already mentioned, and allows you to build more wind and solar such that you can turn off the electrolysis during times of the year that you otherwise would not have enough generation, right? Gives you productive outlet and use for what otherwise would be curtailment. And I'm going to show that in just a moment. And then finally, all the way on the right for the net zero economy case, right? There's 5.5% of our generation mix that's coming from natural gas without carbon capture, right? So we all know that it's the last 5 or 10% that's most expensive in an electricity system. The way that this scenario here solves that problem is just not doing the last 5 or 10%, right? You take those emission reductions elsewhere. So that was the generation side. I want to highlight here kind of the firm capacity that sits behind that. And I'm going to show, like some of my fellow panelists, some of the sub-annual time step in just a moment. So we've got a lot of thermal capacity that's backing the system up. We've got, CTs operating at a 3% capacity factor. We've got CCGTs operating at a 12% capacity factor. And then we've got basically a 45% cap factor for the gas with carbon capture. And even though we've got a slight increase here, that I will note that this is decreasing as a kind of percent of peak load, right? Because you saw that high electrification scenario that's coming into the model at first there. And then I'm going to randomly kind of weave in some insights from Europe as I go along. From what we've seen in our modeling, the kind of need for clean firm, which I would say is a subset of the generation that I showed on the last slide, is very likely to be higher in Europe. And so these are a number of scenarios from our annual decarbonization perspectives as kind of little lines for Europe and the United States. And the big finding here for Europe is that they are more energy constrained than the US, and that's largely because of the potential for onshore wind, right? The wind resource is worse, and also some of the siting constraints are even kind of more dire in Europe than they are in the US. And I'm going to kind of highlight here some of the seasonal balancing challenges that are a little bit different for the US and Europe that makes kind of Europe look especially hard. So this is basically daily electricity generation across 365 days. So you've got the US on the left and Europe on the right. And what you'll see in Europe is the seasonality of renewables, where when you go to high latitudes, if you're in Germany, your solar is not producing very much in the winter, right? That's probably not a surprise to anybody in the room who's ever spent a winter in Germany. Like, unfortunately, I have, yeah. But you can look at the solar there, and in fact the wind also, and you see that difference. That results in this kind of sustained peaking need in winter in Europe, which is quite large, right? So the pink there is gas generation, and you've got in Europe also this larger share of clean firm at the bottom due to the lower wind potential, but also because of the seasonality, right? Whereas in the United States, what we have is kind of both a summer and a winter kind of peak. It's due to the heating, it's due to the air conditioning, and both of those are kind of times of system stress where during certain locations in the U.S. we use our gas power plants. So of the scenarios that I just showed, I want to highlight the electricity sector emissions. So the net zero economy is the blue line there that kind of ends down just under 200 million metric tons. That's about a 93% emissions reduction. And then the net zero clean electricity case, the difference there was $130 billion in scenario present value cost. So that, that was basically the difference in that kind of what I would call an allocational policy of, where do we allocate CCS capacity? Where do we allocate our scarce biofuels? And what's interesting is the economy-wide emissions balance doesn't change all that much. We use more sequestration and power instead of other places. We use more clean fuels and power instead of allocating those to transportation. But the overall kind of balance, I actually am not showing it because it would be hard from that distance to actually tell what the difference was. And here's the impact on rates. So the other point I want to make around the importance of sectoral coupling is, if you're in the power sector and you just want to deal with the power system, that's fine. But there's also an opportunity here through sectoral coupling to reduce customer rates. So this is not, that wedge there, I will admit, is not huge, but that is basically the difference we're getting in kind of, cents per kilowatt hour before and after doing the kind of addition of hydrogen and the other loads I've been talking about. I think one key insight here for the importance of kind of sectoral coupling, because you might wonder, for example, can't you just get the same outcome if we just have really cheap long duration storage or more electricity storage in that system? Can't that provide the flexibility? And I think a key fact here is that based on the fundamentals, the storage cost as we go from electricity to heat from industry and hydrogen to some of the derived fuels such as jet fuel and ammonia, our storage capital cost comes way down, and actually the cost of transporting these fuels also goes way down. So if you look at a hydrogen pipeline versus an electricity DC transmission line, it's about an order of magnitude difference on a dollar per megawatt mile basis for moving those fuels in those two forms. So this is really important. Now, of course, you go from electricity down to these other fuels and you don't go back up to electricity. But the point is, as we showed before, you've done 50% electrification in the economy. You still have a lot of other fuels that you need to take care of from a decarbonization perspective, right? And that's where these things get used. My axis got a little screwed up here, but this is these are the curtailment rates for each of these scenarios. So as Peter mentioned, some level of curtailment is economic, and I will also note that because this is kind of a 28 zone model across the US, this is an underestimation of curtailment because we're ignoring a bunch of local transmission constraints that may be more important than this kind of bulk power system curtailment. But in the clean electricity case, only, we've got, basically 2% more curtailment. We also have this kind of overbuild of the system to take advantage of the IRA tax credits that are, depending on how fast emissions rates come down, expiring sometime in the 2030s, very likely there. On the curtailment front, I just want to highlight one thing, maybe to motivate for some in the room to think about this sectoral coupling sooner rather than later, which is Europe has since 2019 doubled their capacity of solar. And if you look at some of the headlines this year, they're setting records in terms of hours of curtailment across Europe and negative prices. Just like in the US, where we have production tax credits, they have feed-in tariffs. And I think it's very likely that what the situation we're seeing in Europe presages a similar situation we will probably see across the US, where right now the only thing we do seem to be able to build is solar in the US from the Inflation Reduction Act, and that's going in at record rates. And so if we don't think about some of these balancing solutions sooner rather than later, I think it's very likely that in the next couple of years, the US finds himself in a very similar situation. So just a couple more slides here. I want to highlight what I think some of the key technologies for when we are doing integrated resource planning or utility planning. These are some of the key technologies that we've seen in our capacity expansion as very important to include to kind of make sure that we don't have bias in the model towards a certain set of solutions. So the first is the inclusion of these low capital costs, dollar per kilowatt, hydrogen heat technologies with very deep markets, right? So it can't just be hydrogen back to your power plant in a closed loop cycle. And those and the low dollar per kilowatt cost, and there are other kind of opportunistic loads that may emerge in these scenarios, but the low dollar per kilowatt cost is really important because they can operate with low utilization and complement renewables very nicely. The second is the use of clean fuels in existing thermal power plants with minimal new capital cost. So if you've got a thermal power plant that's operating at a 5% capacity factor, you can burn a clean fuel in that power plant, and that's much cheaper than making capital investments in, nuclear, gasable carbon capture. Pick your clean firm technology in many of these scenarios. And then finally, when you do build clean firm, integrating things like thermal storage within that kind of technology, also we've seen that can hugely improve the economics. So, take at the bottom the example of a advanced nuclear reactor. I can have the reactor itself, which is the expensive part, run at a 95% capacity factor. I can put thermal storage in the middle, right? I store the heat coming out of the reactor, and then a heat exchanger, and I have a steam turbine that I can operate at a 40% capacity factor. And I can oversize my steam turbine to provide peaking capacity. That's the cheap part of the system, right? So overall, this thing's operating at a 50% capacity factor, but that will complement a very high renewable system much better than, just thinking about a light water reactor running, flat out all the time. So kind of in summary here, I would say that electricity only overestimates the importance of getting to 100% clean electricity, the cost of getting to 100% clean. It overestimates the amount of electricity storage that's needed on those systems, overestimates the capacity factor of some of the thermal assets, and overestimates curtailment. And then we underestimate some things, which are the percentage of electricity that actually can be delivered from wind and solar, the new megawatts of renewables and potentially new megawatt miles of transmission. It underestimates some of the competition for things like biomass and sequestration, right? Because in the economy-wide scenario, that biomass has a very high use and to make SAF fuels, for example. So if you're putting your biomass into a BACS power plant in the power sector, you're competing with the airline industry for that fuel, right? And then finally, the importance of kind of these market reforms for load participation. I just highlight again that I think these market reforms will become relevant sooner rather than later, both because of the kind of huge amount of solar we're seeing coming in the US, and then some of the other tax credits like 45V that have already been mentioned. So thank you, and look forward to the conversation here. Appreciate it.